So the topic is photosynthesis, which in green plants occurs in the chloroplast. And I remember that I had found a simpler picture of chloroplast. So I put this in the slides just in case it wasn't clear. So now the thylakoids are clearly labeled, and the stroma and the lumen are clearly labeled. So I like this picture a little bit better than the other one. So remember, it's the thylakoid and the stroma and the lumen that are going to be relevant for absorbing light, carrying out electron transport reactions, and making heat. Protons are going to go from the stroma to the lumen, etc. So here's a little bit better picture than one in the book. Okay, so you can look at that. All right, so the first part of this is, and the first part that's covered in the book is light absorption, which I want to say a little bit about. Before I get to that, let me sort of review the light reactions of photosynthesis. What I said last time is that the light reactions basically are a way to carry out the following reaction. It's the reaction of water with NADP plus to make half a mole of oxygen, NADPH, and a proton. And what's the problem? The problem is that the reduction potential of this is minus 0.32, and the reduction potential of oxygen is plus 0.816. So the delta E for the reaction is minus 0.32 plus or minus 0.816, or you could just say you subtract the two, or subtract one from the other, and what you find is that the delta E is minus 1.14 volts. So it's negative voltage, so it confirms that this reaction is not spontaneous, at least not under standard state conditions. If you plug this delta E value into the equation for free energy, the number that I got is that delta G0 prime for this reaction is plus 220 kilojoules per mole. So a very large positive free energy barrier against this reaction. So the only way to be able to use water as a reducing agent, to be able to get electrons out of water, eventually to NADP, is we have to put in some energy, and so we'll use energy from sunlight to enable this reaction to occur. So you could say that's why the plant needs energy from sunlight, is to get this otherwise very unfavorable reaction to go to the right. So the first issue about light absorbance is what is there in the plant that absorbs the light. So let me just comment on these. So what are the light absorbing pigments? The most important is chlorophyll. So what is chlorophyll? So chlorophyll has a magnesium ion, which is bound to 4 nitrogens. The nitrogens are each part of a 5-membered ring. This sounds familiar. That's supposed to be a 5-membered ring. Very well. And the 5-membered rings are connected by 1 carbon. So far it looks a lot like a porphyrin ring, and it is very similar to a porphyrin. At this point I'm going to stop drawing and just show the figure of the book. Because it's very similar to a porphyrin ring, not identical. But here's the structure. This is called chlorophyll A. So there's a magnesium ion, the 4 nitrogens from the 4 5-membered rings. As usual, there's other groups around the periphery of the ring. There's this very long hydrocarbon chain attached, so that overall this molecule is very hydrophobic. In addition, there's this thing here where this is looks like a propionate group, at least started as a propionate, but it's been joined to this additional ring, which both of these additional rings that are not part of a Now, this is a new ring. This is one of the 4 rings, but this is an additional ring that's not part of the porphyry ring. So that's a difference. It's not really that important, but the other important thing is, which outlined in pink, is that there's a lot of conjugated double bonds, and so that makes this molecule absorb visible light. Okay, so chlorophylls obviously are important for absorbing visible light. Now, chlorophyll A has these absorbance maxima. If you take an absorbance spectrum, there's other varieties of chlorophylls. In plants, chlorophyll B is the same as chlorophyll A, except this group is, I guess it's an aldehyde instead of a methyl, and I think that's the only difference. Bacteria have chlorophylls that differ in small ways, right? So none of these details are really that important, although maybe it's relevant that plants do have these 2 different chlorophylls, and they have slightly different absorbance spectra, which is shown in this picture. So here's the actual absorbance spectra of these purified chlorophylls. So the yellow is the absorbance by chlorophyll A with an absorbance maximum at long wavelength, 662, and then another absorbance wavelength down at much shorter wavelengths, still visible wavelengths. Right? And then chlorophyll B has slightly different absorbance maxima, short wavelengths, and another one at long wavelengths. Note that they don't absorb at all in between. Right? And these wavelengths, somewhere in here is where green light is. Right? So the reason green plants look green is that they don't absorb green light, they just reflect it. So that they look green because they're absorbing the bluish light and they're absorbing reddish light. And all this stuff is green. All right, now in addition to chlorophylls, and in part because if the plant wants to use the energy of sunlight efficiently, it wants to be able to capture the short wavelength sunlight and the long wavelength sunlight, but it'd be nice if it could capture some of the intermediate wavelengths. And so there are additional light-absorbing pigments in plants that are collectively known as accessory pigments. And so these are molecules that will absorb light at wavelengths that are not absorbed by chlorophyll. I think that's how you might define an accessory pigment. And various organisms make various molecules. I'm just going to show the structure and draw them. But here's an accessory pigment. This is carotene. Right, so this is it's a long hydrocarbon, but again, you see it's got this long conjugated double bond system. And so again, this is a molecule that absorbs visible light, and so that's found in plants. And there's several molecules that are related to carotene that are referred to as carotenoids or carotenoids. So lutein is another molecule. It's very similar to carotene. Also has this long conjugated double bond. And there's some others that have similar structures. So these molecules have characteristic absorbance spectra, which I'll show in a second. These are some accessory pigments that are actually found in photosynthetic bacteria, currently not in plants. If you look at this, it's actually kind of a heme or a porphyrin that's been opened up into a linear molecule. But this is called phycoerythrobilin or phycoerythrin, and then this phycocyanin that's related molecule. So these are accessory pigments in photosynthetic bacteria. And the last picture is now this is an absorbance spectrum, or a composite absorbance spectrum of chlorophyll. So here's chlorophyll B in green, like what I showed. Here's chlorophyll A in purple. But now they've added this absorbance spectrum of beta carotene in orange, lutein down here in black. And so those expand the absorbance region at least a little bit for the green plant, not really by that much. But you see that there's wavelengths that carotene absorbs that chlorophyll B and A really don't absorb. So it's a way to capture light of more wavelengths. And it turns out that the energy that's being absorbed by carotene is going to help in photosynthesis as well. More impressive is for these bacteria, where this red and blue are these bacterial compounds, which can absorb in green wavelength region. Right? So green plants really, even with these accessory pigments, at least the ones that are shown, green plants really don't absorb light much in this region. Here's the actual colors of the light. So here's green kind of here, red at longer, blue at shorter. And then this black curve is the spectrum of light that actually reaches the Earth's surface. Okay, so the point is that plants have a lot of things, or have these molecules that can absorb light. So chlorophyll is important because it can absorb light. Chlorophyll is also important because there's going to be a single chlorophyll that's going to be able to give up an electron and start the process of getting electrons to NADP. Right? So chlorophyll has that unique role that accessory pigments do not have. All right, so before we get into the details of the process, we should do a little bit of quantum chemistry, which is what happens to molecules when they absorb light. So this is going to be quantum chemistry at the freshman chemistry level. So
There it is. Freshman chemistry level.
what happens, quotes, when a molecule absorbs light. So there are at least 4 things that can happen. 2 of them are very important for photosynthesis, and the other 2 are kind of to be avoided by photosynthesis. So let's consider a simplified model of a chlorophyll molecule where I'm going to make a sort of orbital energy diagram. So let's say we've got energy in, this is a chlorophyll, so let's say this is the lowest occupied orbital in a chlorophyll molecule. And for simplicity, we'll just say that there's 2 electrons in this orbital. So remember, the arrows indicate electrons. And so, this is to represent the molecule in the ground state before it absorbs light. And then there's going to be a, this is the highest occupied orbital. This is not essential. This is going to be the lowest unoccupied orbital. At room temperature, all of the electrons are in their ground state orbitals. They don't have enough energy to get up into these higher energy orbitals. But if the molecule absorbs visible light, the photon of light, of course, carries energy, and so that can be enough energy to excite the molecule. And so the way we draw the schematic, an excited state molecule is that 1 electron is promoted to a higher energy orbital. Right? So this is a way we'll indicate an excited state molecule, and I'll use chlorophyll as star to indicate that it's an excited state. So this molecule has greater energy because it's absorbed this photon of light. So the question is, what's going to happen to that energy? Right? So as I said, there are 4 things that can happen, at least. There are 4 ways that molecule can give up that energy. All right, so the first 2 are the things that don't happen in photosynthesis, and if they did, they would sort of defeat the purpose. So one thing that an excited state molecule in principle can do is it can emit a photon. Right? And so the photon that's emitted carries away the excess excitation energy. Right? The energy came because the molecule absorbed light, but if it emits light back out, the molecule, I put a reverse arrow, the molecule will relax back to the ground state. And the photon travels away. And this is the process that's known as fluorescence. Right, so for photosynthesis, from the standpoint of the plant, that the chlorophyll that absorbed the light, it has all this energy. Fluorescence would just defeat the purpose. It would take away the energy. So that turns out that does not happen in plants. Okay? But that's one way that a molecule can lose excitation energy. The second way that it can lose excitation energy is it can collide with other molecules. The energy can be transferred to the other molecules just by collisions, and the energy ends up as just faster motion of all the molecules in the region. And this is the case, the simplest case, where the energy is dissipated as heat. All right, so this molecule loses the excess energy, it goes back to the ground state. Neighboring molecules acquire a little bit more energy, and it, you know, spreads out until the energy is gone. Right, so that's also bad. That's not going to help. That's not going to help to get electrons from water to heat. Right? So these two things, in fact, do not happen. It's because the photosystems in the plant are set up to have better and more efficient ways of dealing capturing and holding the energy in the excited state. Right? So let's say this was one thing that could happen. This was the second thing that could happen. So what's the third thing?
So there's no energy diagram for this, right? Just saying energy loss is heat.
Yeah.
That's a bridge. Oh boy.
So the third thing that can happen is called exciton transfer, and this is where it's a quantum mechanical phenomenon, so we won't really try to explain what it is, but let me just describe how we can illustrate this. So we have our chlorophyll in the ground state. It absorbs a photon of light, and sorry, let's call this chlorophyll number 1, because now we need 2 chlorophylls. It absorbs a photon of light and becomes excited. All right, so again, it has this excess energy. So exciton transfer is a process whereby if there's a second molecule that's very close to the one that became excited, and it doesn't have to be a chlorophyll, but let's suppose it is. And this chlorophyll is in the ground state. The excited state chlorophyll, the energy in the excited state can be transferred from chlorophyll 1 to chlorophyll 2. And so the result is that chlorophyll 1 relaxes back to the ground state, and chlorophyll 2 now has the excitation energy. So now chlorophyll 2 is chlorophyll star. And so this is a very important process in photosynthesis. The result of this is that the excitation energy that was originally in one chlorophyll is still there. It's in a different chlorophyll, but at least it wasn't lost as heat or as fluorescence. Yes?
Is this like the same thing when you have like overlapping orbitals and
I think it does not require orbital overlap. I could be wrong. This is known as Forster energy transfer, or FRET. For us, it's resonance energy transfer. The one thing is that these molecules have to be very close to each other, right? Because there's a very strong resonance. All right, so this turns out to be very important. This doesn't really help electrons, at least in a direct way. It doesn't help get electrons to NADP. But it's the fourth thing that is really most important. For getting electrons to start flowing. So the fourth thing is called photooxidation. And for this, again, let's start with a chlorophyll. It's called chlorophyll 1. It's not the same chlorophyll necessarily as above. But now this is a special chlorophyll, as I'll elaborate on later. This chlorophyll has some acceptor molecule that's next to it. So I'm going to arbitrarily, I'll just call it acceptor. And the acceptor is in a ground state. It has a an excited state orbital or unoccupied orbital. And the important thing is that this orbital energy can't be higher than this energy, right? So let's suppose the chlorophyll becomes excited. So this chlorophyll could be excited by absorbing a photon directly, or this chlorophyll now could be excited via exciton transfer, right? So the excitation energy is going to have to find its way to this one particular chlorophyll. And if so, this chlorophyll becomes excited. It has an electron in this high energy orbital. And now the energy of this orbital is higher than that one. And so it's possible that this electron can be transferred from this orbital to that one. In other words, the electron goes from this excited state chlorophyll to this acceptor molecule. Okay? So if that happens, this is now, you can think of it as transfer of energy, but it's actually transfer of an electron. And so the chlorophyll is left with only one electron. The acceptor has an extra electron, right? So it's an oxidation process because the chlorophyll lost an electron, right? The chlorophyll, which was in the excited state, now only has one electron in this orbital anyway, and so we should call it the plus sign to indicate that it's got a positive charge because it lost an electron, right? So this is an oxidized chlorophyll. And the electron is now carried by the acceptor, so we could put a minus sign to indicate the acceptor now has a negative charge, but this is a reduced acceptor. So it's photooxidation, it's an oxidation process, but it required the energy of light to first excite the electron donor so that it has enough energy to be able to donate the electron to the acceptor molecule. So this is how electrons are going to end up getting to NADP. This electron, which originated in chlorophyll, not in water, we'll come back to water yet, but this electron will eventually be transferred to NADP. And that electron will be used to reduce NADP to NADPH. This chlorophyll has lost an electron. It needs to get one back. So where's it going to get it back from? Eventually, it's going to get an electron from water. Right? So you could say that water is being used to reduce this chlorophyll back to where it's started. I'll show the details of that in a minute. But this is photooxidation, and this is what again initiates the electron transport process of photosynthesis. Any questions about that? Yes.
Did you say that the initial excitation of the chlorophyll electron was due to exciton transfer?
I think it's most commonly that it is, because again, this is one particular chlorophyll, so we'll see there's a lot of them. I think it's most likely that it is, but I think in principle that it could be direct absorbance of the chlorophyll. Any other questions? All right. This is sort of the outline of what happens. This is now a cartoon that shows more specifically how this works. So this picture is a picture of what's known as a photosystem. So let me try to describe these. So in green plants, there are two different types of photosystems, photosystem 1 and photosystem 2. But photosystems are assemblies of a large number of proteins plus what I'll call pigments, pigments being chlorophylls but also accessory pigments. And they are found in the thylakoid membrane in chloroplasts. So they have a lot of pigments that can absorb light. As part of the photosystem is something called the reaction center. In this cartoon, the reaction center is this sort of barrel-shaped thing. And this whole thing represents the photosystem. This barrel-shaped thing represents the reaction center. The reaction center contains what's referred to as a special pair of chlorophylls. And these special pairs, what's special about them is that these are the chlorophylls that actually become photooxidized. So so these are the source of electrons that eventually reach NADP+. So there are other chlorophylls that in the surroundings, those do not become photooxidized. Those instead become excited and can transfer energy around by exciton transfer. So in this cartoon, here's the reaction center, and then there's accessory pigments and chlorophylls out in the periphery. You know, sort of the cartoon version is that this molecule absorbed light, became excited, and then energy was transferred. That's what these little arrows represent. These represent exciton transfer among these different molecules until eventually the energy has to get to the reaction center. And so it shows exciton transfer and then implicit is the oxidation. So there's some pictures in the book that show structures. I think the next slide. So this is a close-up. Here's a picture from the book that shows the structure of a photosystem from a bacterium, cyanobacteria, also known as blue-green algae. So I think there are three. This is sort of a trimer. So there's three copies of this assembly. So I think the picture in the book, yes?
In the center of the green, where they only see the first
No. Turns out. Here's what this is an expanded view of just this part of this trimer. And the gray stuff is proteins. Right? And so what they've done in some pictures from the book is they took away all the proteins, just using a computer, and they left behind only the pigments. And it's to show that there's a lot of pigments. I think the greens are chlorophylls. You can kind of see the porphyrin-like rings. The yellow are these other carotenoid molecules. You can see very long. And the special pair of chlorophylls is right in here. So there'd be a special pair in here. And I think that's another one here, another one here. So I guess there's three of them in this assembly. So the reaction center in this molecule is right here. Right? And then the rest is what are going to be known as antenna chlorophylls. So this is from a bacterium. This is from the book. Let me show a picture that's a little more recent. This is from a green plant, pea. And so this is what photosystem 1 of a plant looks like. This is from an article that came out about a year ago. So someone determined the three-dimensional structure of this thing. So let me say a little bit more about what this is. This is complicated, but you see these cylinders represent alpha helices. So wherever you see a cylinder, that's a protein. And they've given them different colors because there's a bunch of different proteins. Right? There are two types of proteins that make up these, the photosystem, sort of independently of the, in this picture, they've labeled them in two different ways. Say there's one type. So proteins that they've labeled PSA, those are the ones that are up here. Those are part of what they're calling the photosystem. The ones down here that they labeled LHC, that stands for light harvesting complex. Okay, so the idea is that, as I'll show in a minute, you can see all this sort of green and yellowish stuff in there. Those are chlorophylls, et cetera. I'll show them in more detail. The idea is that the reaction center here is up here, I think, or it's either here or here. This so-called light harvesting complex, these are proteins that have chlorophylls bound to them. They harvest light in the sense that any of these things can absorb light. Right? And again, the energy, the excitation energy, if it's absorbed in one of these, has to find its way up to here. So how does it get there? It gets there by exciton transfer. Okay? So the idea of light harvesting complex is that there are proteins that have themselves have a bunch of pigments bound to them. So this is a picture from the book. Again, the protein is in gray, and now you can see that this particular protein has a lutein molecule in yellow, several chlorophyll molecules, right? So its job is to just absorb light. Right? So there's a ton of stuff that they can absorb light. Right? These chlorophylls are often referred to as antenna chlorophylls. You can think of them, they're up on the roof, they're absorbing light, and then they're just absorbing light to get the energy down into the reaction center. Right, so back to this picture. This is a pretty remarkable structure. It contains, there's 16 different proteins of both types. There are 155 chloropylls in this thing, in photosystem 1. There are 26 beta carotenes, 5 luteins, 4 of this thing. Violazanthin is another kind of carotenoid molecule, so there are 4 of those, it turns out. And 3 iron sulfur clusters, so those are going to help get electrons where they need to go. And phyloquinone is a quinone. It's sort of like coenzyme Q. And we'll come back to it later. It turns out there are 2 of them in there. And that might be about it. Okay, so there's a lot of components, a lot of things that can absorb light. And then let's look at the structure. So this is one view of the structure. This is sort of a side view. This is where the membrane is. Right? You can kind of see it's got a flat top and a flat bottom, so it's sort of is inserted in the membrane. It's got this little bit that pokes out onto one side. So that's how it sits in the membrane. And then finally, let's take this picture, which shows all the proteins and all the pigments, and again get rid of all the proteins. And so then this again shows this very complex assembly of all these molecules that are set up to be able to absorb light and to be able to transmit that excitation energy from wherever it gets absorbed here. Right? So these, right in there is where the photooxidation actually occurs. Right? So that's, in this molecule, that's where the reaction center is. So it's a very large, complex assembly of stuff. All right, so now we know all the things that are involved, and now I want to spend the rest of today and some of the next time going through the pathway of where do the electrons actually go in this process. So this is a cartoon version. Right, this is another cartoon, but it shows a little more detail. So this is a cartoon of photosystem 1. This brownish thing represents the photosystem. Down here is more photosystem. This represents a photon of light that gets absorbed here. Right? And so in this picture, the red arrows represent transfer of energy in this system. So the energy is transferred via some pathway, and the exact pathway depends on where the light is first absorbed. But the energy is being transferred until it reaches this special pair of chlorophylls. So that special pair of chlorophylls, that's the reaction center. So I think everything in here represents the reaction center. So that's the chlorophylls that once they're excited, they can give up an electron and become oxidized. And so the blue arrows, as I indicated, now the blue arrows emanating from there represent a path of electrons. And so electrons are going to be transferred from this special pair of chlorophylls down to this protein called pyridoxine. The red things represent iron sulfur clusters. Actually, this might just be iron. These red-orange things are iron sulfur clusters. So there's going to be an electron transport chain that's going to take electron from here, transfer it via these carriers, and eventually reaches a small protein, and that protein can then diffuse away and carry away the electron. So the photooxidation process actually occurs in this reaction center. And the photooxidation, which is again this sequence of arrows, is a way to take an electron out of this excited chlorophyll and very rapidly and very efficiently take the electron and get it out of the reaction center. And make sure that the electron that comes out of that chlorophyll doesn't go back into it. Because if it goes back in, then you're back to where you started. And so plants are very efficient at capturing that energy and using it to get electrons out. All right, so the chlorophyll, this is now to represent the special pair. It's one of the chlorophylls that are part of the special pair. So let's assume it has been excited. So it's in its excited state. And so then there's going to be an acceptor next to it. And the acceptor that's next to it is another chlorophyll, according to this picture. Right? So that's what this represents. That's going to accept the electron. So this chlorophyll was in the ground state. It's going to accept the electron from this one. And this electron transfer happens very, very rapidly. The slide I'll show on the next slide says that it takes about 3 picoseconds, which is 3 times 10 to the minus 12 seconds to get the electron from here to there. So that's very quick. Next to this chlorophyll is the next carrier, which is what? I guess it's another chlorophyll. Right? And so this is currently not quite as fast. Well, I'll show the picture. All right, so each of these molecules becomes alternately reduced and then oxidized. The picture in the book shows this for a bacterium, a purple one. This is the photosystem in these bacteria. This is a very simple photosystem. But the nice thing about this structure is that it was used to analyze the details of the electron transport. So in this case, the special pair is here. So there's a chlorophyll, 2 chlorophylls right here. If they become excited, the electrons are transported by this process. So I'll just show the steps. All right, so in 3 picoseconds, the electron goes to this molecule neighboring, which is a chlorophyll. Right? So 3 picoseconds. Takes a little longer, 200 picoseconds for the electron to get from this molecule to this quinone molecule. So again, it's similar to coenzyme Q. So that's this blue arrow. Takes a little bit longer for the electron to get from this quinone to that iron. 6 microseconds. Okay. Right. And so these electrons have been carried away from where they started. Eventually, the quinone is they're going to be given the ferroxide. Now, meanwhile, this chlorophyll is oxidized, right? It's a chlorophyll plus, right? So it needs to get electrons from somewhere. So the other part of this photosystem is that there's a way to get electrons into here, and in this photosystem, it turns out there are hemes. So the chlorophyll is going to get an electron back via this sequence of hemes. And where those electrons come from, we'll discuss in plants. I don't know about bacteria, right? But this shows, this is a figure from the book that shows you in detail what's going on to initiate the sequence of transfer. Let's go back to green plants, which is what I want to focus on, and let me talk about sort of the bigger picture of green plants. So, photosystem 1 has a chlorophyll, which is referred to as P700. So this is the special pair of chlorophylls. It's called P700 because it has an absorbance maximum of 700 nanometers. Right, so that's a terminology, and you'll see that on the slide. But this represents the chlorophyll that's going to become photooxidized. Right, so electrons are going to be transferred from the chlorophyll to ferredoxin in the oxidized form, and the ferredoxin will accept an electron and become reduced. Meanwhile, the chlorophyll has lost an electron. So in green plants, the chlorophyll becomes reduced again by a protein called plastocyanin. Which, before it gives up an electron, is in its reduced form. And the plastocyanin becomes oxidized. All right, so this is the electron that's going to replace the electron that the chlorophyll lost. Again, the ferredoxin, eventually the electrons, and you're going to need two of them, but eventually the electrons are going to be used to reduce NADP plus NADPH. Okay, I think I said all this. But here's again this picture. So here's a special pair of chlorophylls, one electron at a time, one electron per photon. One electron travels from here to the ferredoxin. So now you have reduced ferredoxin. Here's plastocyanin. Plastocyanin is then going to transfer an electron to the chlorophyll to replace the one that was lost. So that's what goes on in photosystem 1. All this. All right, here's the slightly bigger picture now of some of the things that I just said. So here's photosystem 1 in the thylakoid membrane. Right? So this is the thylakoid membrane. Here's the lumen of the thylakoid. Here's the stroma. So there's photosystem 1, and it's absorbing light and transferring an electron to ferredoxin, but then eventually to NADP plus. So you could say that photosystem 1, you could say that it performs the following reaction. Let's refer to the P700, the specific chlorophyll. Because you need 2 electrons to reduce NADP, you're going to have to absorb 2 photons. But that 2 photons will cause 2 electrons to come out of P700, and that's enough to reduce the NADP. Right, so you could say that photosystem 1 catalyzes this reaction. You need a proton. And that'll give us 1 NADPH. So you could say that's what's going on here. Ferredoxin is just an intermediary to get the electrons from the P700 chlorophyll to the NADP. We're left behind with the oxidized chlorophyll in the photosystem 1. We need to reduce that. This is where photosystem 2 is relevant. So this is the second photosystem in green plants. And that's in this picture, that's what's shown here. So there's photosystem 2. And photosystem 2 is structurally very similar to photosystem 1 in that it has lots of proteins and chlorophylls. Photosystem 2 will do the following reaction. The special pair in photosystem 2 is called P680 because it absorbs light at 680 nanometers. So they call it. They don't explicitly show P680. But P680 is the chlorophyll in photosystem 2. And so we're going to need 2 electrons to reduce the oxidized P700. So what photosystem 2 does is it initiates an electron transfer process where electrons are transferred from photosystem 2 through some intermediaries that we'll say a very little bit about. But electrons are flowing from photosystem 2 through these intermediates, eventually to plastocyanin, but they're going to find their way to photosystem 1. And so the result of this is photosystem 2 now becomes photooxidized. Photosystem 1, the chlorophyll in photosystem 1, is reduced back to its ground state. So photosystem 2 exists to provide the electrons that were taken out of photosystem 1. Where does photosystem 2 then get electrons from? Photosystem 2 is going to get electrons from water. Right? And so the other thing that photosystem 2 does is it catalyzes now this reaction where water plus oxidized P680 goes to half a mole of oxygen plus 2 P680s. Reduces P680 back to where it started, ground state, and I guess it's the protons. Right, so in plants you have these two photosystems that carry out the process of taking electrons from water, give it to photosystem 2, electrons go from photosystem 2 to photosystem 1, and from there to NADP. Right, so that's the whole process that occurs in plants. This is one cartoon way to show it. There's another very standard way of showing it, which is what's known as the Z scheme. Right, it's called the Z scheme because it looks like the letter Z. And so I'll just finish here. So this part of it represents photosystem 1. Here's P700. There's excited state of P700. There's ferredoxin. There's NADPH. Right? Here's photosystem 2 on the left, P680. Electrons are going to go from P680 to P700, and here's water. So this is a way of diagramming the connections between these two things. But the other thing it diagrams is reduction potentials. Right? Notice that the y-axis here is not for illustration. This is a quantitative axis that shows reduction. So I'll come back to the Z scheme and fill in some of the gaps of what I said and finish a little bit that I want to say.